Hi, in this class, I'm going to simulate surface code with Python. So here you're looking at the Python code that I implemented the surface code with the network X package. And I'm going to begin with the perfect matching. So I'm not going to explain all the details of my code, but I will going to deliver the core idea, and whatever is missing will be covered in the next Wednesday class. All right, so this code block is implementing perfect matching. So when I run this code, there are two pictures appeared after running this code. And you can see that they're actually the same graph, and they differ by the pair, which represented by these red edges. So look at this first picture here, and there are 4 by 4 vertices, total 16 vertices, and they are connected by edges in the lattice configurations, but there is red edges or highlighted edges, which pairs the vertices in perfect way, which means that there's no vertex left behind. And this is actually a maximum weight matching, which means that you can see that there are weights on every edge. So if you add all the weights on the edges which are highlighted in red color, then the sum is the maximum among all the weight sum of collection of edges which pairs the vertices in perfect way. So let me say it again. So these red edges is maximum in a sense that if you add all the weights of those edges, then it is maximum among all the possible ways of matching the vertices with edges. So this is maximum matching. So this is called kind of maximum weight perfect matching. But we actually want the minimum weight perfect matching. We'll explain why that is the case. So if you want to go for the minimum weight sum, then you have to change your pairing. So this graph and these weights are randomly generated, and there is an algorithm to finding the minimum weight perfect matching, and I used that algorithm already implemented in the network X package. And these red edges are the set of edges that gives you the minimum value of the sum of weights. Okay, having said so, we're going to show you the surface code. So here I defined a lot of functions that create surface code and simulate surface code. Here you can see the simulate defects and draw surface code and draw error chains and find chains, and you can even see the simulate surface code right here. Okay, and error correction parts and checking answer parts. So I'm going to skip all these details. I just want to show you the picture. So here, let me give the size of my surface code to be 4, right? And here you can see that there are two pictures as I run this function, simulate surface code. The left one has auxiliary X and auxiliary Z attached to the top and bottom and left and right. So this will be explained later why we need this, but first let's just focus on the inside. So on the right hand side, you have a picture which only consists of circle and squares, and here the circle means the data qubit and square means the stabilizer qubit. And on the left, you can see that the data qubit has been indicated if it has an error, X or Z or Y. But on the right hand side, there's no data qubit indicated by its error. So we simulated error with a 10% of error rate. You can see that 0.1 means the 10% here. That's why we can not only generate the error, but also we know where the error is. But when you make an error correction in the quantum computer, you don't know where the error occurred. You only can guess where the error occurred by measuring the stabilizer. So on the right hand side, that's the thing we can actually detect. So the only thing that we can detect is that there has been whether a change in the measurement outcome of the stabilizer qubit. So on the right hand side, it says that there has been 4x stabilizer right here that has changed its value from the previous cycle, and 1z stabilizer that has changed its measurement outcome. And that is because of these four errors. Because there was a Z error on this data qubit, the X stabilizer has been turned on, and because there has been a Z error on this data qubit, X stabilizer right here has been turned on. And because there has been an error Y on this data qubit, the X stabilizer on left and right has been turned on, and the Z stabilizer on top and bottom has been turned on. But in real life, the bottom Z stabilizer has been not turned on because the X error has been occurred on the data qubit right here. So therefore, this X error has turned Z stabilizer on the left again. So the Z stabilizer has the same value as this previous cycle. So in the readout, we see that the Z stabilizer has not changed its value from the previous cycle. So these 5 stabilizer is all we can see as the from the syndrome measurement here. So let's look at the result. So we took the error correction, which means that we guess where the error has to be in order to make this readout to be back to normal, back to the original. So look at the left figure here. So this is trying to correct Z error. Okay, so we see that there are 4 X stabilizer turned on, right? So which means that this readout has been changed from the previous cycle. So in order to correct this, or in order to guess which data qubit had an error, had errors, Z errors, which makes this X stabilizers, 4 X stabilizer turned on. And the algorithm concluded that these data qubit and these data qubit, the Z error on these two data qubit could make this 4x stabilizer turned on. And that is the most probable way of guessing it. And that's because it uses the minimum number of data qubits to correct error, right? But in fact, what happened was there has been 3 data qubits not overlapping any of the new data qubit that we found to be the candidate that actually occurred at that error. So in real life, instead of turning off these Z errors on 3 data qubit, we actually accidentally turned on the errors, the Z errors on new data qubit, which had no error before. So we kind of have this chain of Z's error from here and way down here and then up here again. So we basically have more Z error than before. So let's move on. Let's talk about the implication of this later, and let's move on to the X error. So in X error case, we only have one Z stabilizer, right? We have one Z stabilizer right here, and the only way or the most probable way of guessing where the ZX error has been occurred is to guess it to be this error, this data qubit. So if you have X error on this data qubit, then this Z stabilizer is the only Z stabilizer that is turned on. However, the same thing applies here. Because we had two X error already occurred in these two data qubits, instead of turning off or removing X error on these two data qubit, we made more X error. So these two data qubits has original X error. This one has artificial X error. So basically we have also the chain of X errors from here to here. Okay, so let's check answer. So the answer means that we have to examine whether our error correction is successful or not. So on the left figure, it checks whether our Z error correction has been successful or not. And on the right figure, it checks whether the X error correction has been successful or not. So you can see that there are 5 Z errors occurred compared to the previous cycle because there has been 3 already, but we made 2 more. So basically, it seems like it's a failure because we failed to identify where the Z error has been occurred, but you can see that the edges are colored in yellow, which indicates that this error correction is successful. Why? So because this Z error is not changing the eigenstate of the logical qubit stored in the surface code. And we're going to talk about this more deeper in the Wednesday class, but if I just briefly mention why this is not a failure, is that if you have Z chain like this one that's starting at the top edge here, or top boundary, which is rough boundary, and ending at the same boundary, then this Z chain is commutative to any of X chain that is running from the left bound to the right bound, because it has to be intersecting at most, or at the even number of data qubits. So if you want to make a logical qubit from the surface code, it means that you are coming with, this logical qubit is equipped with logical X gate and logical Z gate. And we explain that this logical X and logical Z is a chain of X and chain of Z, right? And these chains has to intersect at odd number of qubits. But if it intersects with the even number of qubits, then it's not anti-commutative, it's commutative. And in order to any kind of logical gate to be served as X gate or Z gate, it must satisfy anti-commutative equation. So if you intersect with the even number of data qubits, then it's not anti-commutative, therefore it cannot be served as X logical and Z logical, which means again that this is not changing any quantum state as if it's acting on X or Z gate. So therefore, it's considered to be the original quantum state, original logical qubit. So therefore, we assume that this is not a failure. And the same reason applies to X error correction. So here it's the chain of X errors starting from the right boundary, which is the smooth boundary, and the same smooth boundary on the same side. So therefore, it's also successful. It's success, even though the actual error is occurred, and we couldn't remove it. It's the final quantum state stored in the data qubit is considered to be the same quantum state from the previous one because this chain of X is not acting as a logical X gate. So you can see that I concluded it is true that the error correction is successful. So I'll give you another example. In this case, a bigger um, exercise. So let me increase the number or size of the surface code to 6. And you can see that there is how many 6 errors occurred, and on the right hand side you can see where the stabilizer has been turned on. So there are 4x stabilizer turned on and 4z stabilizer turned on. So you can now just using eyeballing where x error and z error must be applied, must occurred in order to make this result. So think about the Z error first. So these 4x stabilizer is because of Z error nearby data qubits. So the same reason, same thing applies. So the best way of predicting the Z error is just selecting the data qubit in between these pair of X stabilizer. So let's check if my algorithm um, concluded the same way. So look at this X stabilizers here. So I conclude, so in the original, the error has been occurred in these 2 data qubits. So in the horizontal way here. But my algorithm guessed that this Z error occurred in these 2 data qubits, which had no error, right? So because of these 2 artificial error, there has been a loop of Z error occurred. And look at the Z error also, X error on the right hand side figure. So I conclude this algorithm concluded that there has been an X error on this data qubit, which is true. Therefore, my artificial X error has cancelled the actual error occurred in this data qubit, and same for this data qubit. However, my algorithm has wrongly concluded that this this data qubit has had X error in, instead of these 2, right? Instead of these 4, right? So you can go back to our original problem here. The X error has been here, 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 right? There are 4, right? Because of these 4 chain of X error, there is no Z stabilizer turned on up until the end of this chain right here on the bottom here. So it's very low chance to have 4 data qubit had X error in a row instead of 1 data qubit had X error, just to make this Z stabilizer turned on. But when you take a when you make an error correction, you have to go for the largest possible chance, not the smallest, right? So it's very probable, it's very logical to conclude that this data qubit had an X error instead of these 4 data qubit had all the X error here. So therefore, the conclusion is if we check whether our error correction has been successful or not, it is successful because instead of having failed, although we failed to identify the Z error exactly, but what happened is we made a loop of Z error, which again, this Z error is not serving as Z logical gate because whenever you took X chain running from top to bottom, it will intersect even number of data qubits. Therefore, it's commutative with X errors or X chain. So it's not a proper Z gate. Therefore, it's not acting as a Z gate, which means that the quantum state stored in the data qubit is the same quantum state and considered to be the same quantum state or logical state of the previous one. And the same thing applies on the right figure here. We have X chain, and it's starting from the rough boundary on the right and ending at the same side. Therefore, it's still considered to be successful because it's not changing the logical state. So I want to give you when it's not successful. Let me increase even more. So it's now 8 by 8, and let me show you the error correction here. The result is right here, and you can now see that so on the right hand side, on the left hand side, it's the Z error correction, and on the right hand side is X error correction. So on the left hand side, let's look at the left hand side first. There are two types of Z errors or Z chains. One is on the yellow and the other is in red. So yellow one is loop, so it doesn't change the logical state. But on the red one, so if you follow the Z error, X stabilizer, Z error, X stabilizer, always in this chain, then you can see that this chain starts from the top rough boundary to the bottom rough boundary. So it doesn't matter whether it took a long detour, as long as it starts from one rough boundary to the other rough boundary, it will serve the same way as the Z error or Z gate, Z chain, right from the top to bottom in a straight line. So therefore, by applying this Z chain, you assume that the original quantum state, the logical qubit, has changed its state as if the Z gate is applied to a single qubit. So therefore, instead of rid of this Z error or reverting all the data qubit into the original state, we altered our data qubit or altered our logical state to the quantum state we get after applying the Z gate. So therefore, it's false. So we couldn't correct error. But on the right hand side, if you look at the X chain, it consists of only one type, which is half loop in yellow color. So therefore, it is successful. Right? And now, overall, is it successful or not? It's not successful. It's failure because we failed to correcting the error Z error. Right? We want to correct X and Z error at the same time. So if we fail to correct any one of types of error, then we consider it fail. Okay, so there are many other things that I didn't explain yet. So let me go for explanation of this auxiliary here. So how do I find which data qubit has to be selected as the data qubit that had an error in order to correct an error? So we go for in here we need perfect matching. So we want to pair our stabilizer so that which had the red mark, which had a change, so that we can detect an error or guess an error. But we want to go for the minimum weight. In here, minimal weight means that we want to use as small data qubit as possible, right? So if you could choose 2 data qubits instead of 3 data qubits to get the same result, we will go for the 2 data qubits, right? Because if we say these 2 data qubits have been occurred, then the probability of that occurred is p squared. But if you assume that 3 data qubit has had a error, then the probability of that having that error is p cubed, which is way smaller than p squared. So therefore, we always go for the minimum number of data qubit that it has to be an error here. So why do we need auxiliary here? Why do I use auxiliary? Because it's not a problem if you want to find the error um, inside of this surface code, but it's problematic when we have stabilizer turned on the boundary, right? So for example, look at the bottom figure here. So we want to say to turn on this X stabilizer right here, we want to say the data qubit right here, the below X stabilizer had Z error. But then the problem is, in order to use the perfect matching, I need to pair up this stabilizer with something else, right? So this auxiliary X is doing its role as a counterpart or the partner of this X stabilizer in order to make a pairing. And this pair gives you the guessing of the Z error on these data qubits. And so here there's no more question, but same thing happens here. In X error correction, you can see that there is a guessing of the X error on these data qubits and this data qubits, and these both cases are selected because we concluded that pairing this stabilizer and this auxiliary stabilizer will be the minimum will give you the minimum number of data qubit that had X error in order to make this Z stabilizer to be turned on. So this kind of thing is why we need the minimum weight perfect matching in the surface code. So I will show you this picture in the Wednesday class again. So if you have more questions about this, let me know at that class. And we're going to go deeper into the perfect matching algorithm. And then we're going to talk about more logical qubit in the surface code. So the power of surface code is not lying on the effectiveness of error correction, but also lies in freedom of making a logical gates. So we can not only make X logical gate or Z logical gate, we can also make a CNOT gate, we can make Hadamard gate, and many more. So we're going to talk about this throughout the rest of the semester. So thank you for watching and see you on Wednesday.